right, here's a couple more examples of limiting reactant type problems that you might expect. So in our previous video, we looked at a free response question where clearly they gave us the amount of both reactants. We had to figure out what the limiting reactant was, how much product was going to get made, and then how much of the excess reactant was left over. And then in the second problem, we looked at a multiple choice type scenario where again they gave us the concentration and the volumes of the reactants of both reactants. We had to figure out which one ran out first and then use that limiting reactant to figure out how much product we got. So in this example, it says a scientist heats a sample of a pure nonmetal Q in a closed container containing pure nitrogen gas. The reaction proceeds to completion. The unbalanced chemical equations here give the value of each stoichiometric coefficient. So we do see N2, N2, and then we see Q2, and then we see a 2 right here. So A equals 2, B equals 1, C equals 1. And then B says, so here's a different type of limiting reactant problem, is now they're going to show us the actual particles themselves. So it says a particulate representation from before and after the reaction is shown below. The contents of the container before the reaction are represented in the box on the left, and the contents of the reaction after the reaction are shown on the right. A student claims that nitrogen is the limiting reactant. Do you agree or disagree? So Q clearly is the black sphere that's filled in here. So that's Q. And then we've got, of course, it's a diatomic molecule, so those are our N2s. Okay, and then we can see that from this equation, this is a good way to help you understand limiting and excess reactants. We can see that after the reaction is done, again, here's our N2Q2s. Okay, it looks like we've made 4 of them. It doesn't matter how many of them there are. What's important is to notice what's left over. Okay, and you can see that there's 2 of those Q atoms that are left over that did not react. And therefore, what is that telling you? It's telling you that Q is therefore the excess reactant. And if Q is the excess reactant because there's some left over, there's some extra, then absolutely that means that all of the nitrogen got used up to make this N2Q2, and therefore it is the limiting reactant. So do you agree or do you disagree? Absolutely, I agree. Okay, and then justify your answer. You could say because all of the N2 molecules became or were used to form N2Q2, and you can even say and no N2 molecules were left over. Okay, and you could probably go at it from the Q point of view as well. You could say, of course I agree N2 is a limiting reactant because there's some Q left over after the reaction got finished, which signifies that Q is the excess reactant and N2 is therefore the limiting reactant. Okay, example 4, this one's a little bit tougher, says, so it has nothing to do with the previous problem, completely separate problem here. It says 10 milliliter samples of HBr of various concentrations are added to samples of E in a closed test tube. The samples of E react with HBr and the H2 produced is collected in a gas collecting tube as represented by the following balanced equation. Okay, so it's already balanced for us. So here we can see that the initial number of moles of E are different, but the concentration of HBr stays the same the entire time. Okay, and then we can see, so again, one reactant, information here, another reactant, information here. The volume of H2 produced, notice that that number does change from trial 1 to trial 2. Okay, the data from all 3 trials are given above. A student claims that HBr is the limiting reactant in trial 1. Do you agree or disagree? If HBr were the limiting reactant and you started with the exact same amount of HBr in both trials, if HBr were the limiting reactant, that would mean that when HBr ran out, the reaction would stop. And if that's true, then your volume of H2 would be the same for both trials. Because the concentration of HBr is the same for both trials, if HBr were the limiting reactant, then the amount or the volume of hydrogen produced would also have to be the same. Because when you run out of HBr, if it's the, again, what it says down here, if it is the limiting reactant, that means the reaction stops when that runs out. So if the reaction stops when you have 0.5 molar HBr and 0.5 molar HBr, when both of those run out, then again, your volumes of hydrogen would end up being exactly the same. Okay? However, notice that the moles of E do change, and that causes the volume of hydrogen to also change. And if that's the case, if when these changes, this changes, that's telling you that when the moles of E run out, what does the reaction do? It stops. Because in this case, when you had a little bit more E, notice you got a little bit more of the volume. Again, that shows you that as that reaction proceeds, that it runs out, that when that E runs out, the reaction's going to stop. So do you agree or disagree that HBr is the limiting reactant? Absolutely, I disagree. Okay? And again, how would you explain that? You would say that, again, you could talk about HBr that say by when the concentration of HBr remains the same, the volume still changes of H2. Or you could say something about as the moles of E increase from trial 1 to trial 2, the volume of H2 also increases. And and again, that shows that it's E that when it runs out, that's when the reaction stops. Okay, so again, no real math there, but just more of a thinking type question with limiting reactants. So we've seen pretty much 4 different types. We've seen a regular long response or free response type question where you have to identify the limiting reactant, figure out how much product is going to get made, and then how much is going to be left over. Again, a typical multiple choice question with limiting reactants, a particle diagram with limiting reactants, and then a table showing different amounts and you being able to look at that and identify the limiting reactant. And if you can understand those 4, you've got a good understanding of limiting reactants.